Hi, welcome back. Today we're going to talk about three rules for quantum numbers. Let's see if we can answer this set of questions. Which of the following sets of quantum numbers are valid? The first question shows us that we have an energy level of 1, a secondary quantum number of 0, the magnetic quantum number of half, and spin quantum number of half. This is not valid because the magnetic quantum number does not exist as a fraction. Second question, energy level 3. Is it possible to have these four quantum numbers? Yes, it is. Next question, energy level 2. Can we have a secondary quantum number of 2 if the energy level is 2? No, it's impossible. The values of L do not go past n minus 1. So the highest value of L would be 1. How about this set? Energy level 4. So the L value is okay. The ML value goes from -3 to +3, so that's okay. And it is possible to have a positive half spin, so that's valid. Energy level 3, it's possible to have a L equals to 2. It's possible to have a magnetic quantum number of 1, but it's impossible to have a whole number in the spin quantum number. They have to be either positive half or negative half, so this is not a set of valid quantum numbers. By now, you probably have noticed that this diagram is very useful. It shows us the patterns that exist in the periodic table. You've also probably noticed that the periodic table has this distinct shape based on where the s, p, d, and f orbitals are located. But why is there this discrepancy in the energy levels? You see a 3s and a 3p. That corresponds with the third energy level. And then there is the 4s and then a 3d, followed by a 4p. That doesn't seem to follow. Shouldn't this be a 4d? Well, actually, it shouldn't. Each energy level can be divided into subshells. So the number of subshells for each energy level corresponds to what number the energy level is. So energy level 1 has 1 subshell, energy level 2 has 2 subshells, and energy level 3 has 3 subshells, and so on. These subshells have different potential energies, and as you can see, some of the potential energies overlap. So the 3D subshell has a higher potential energy than the 4s subshell. Now when you look at the periodic table, you can see that the energy level 4 starts off with the 4s orbital, then it's followed by the 3d orbital, which is then followed by the 4p orbital. Notice how 4s comes first, then the 3d, then the 4p. We can see this applied in the Aufbau principle. An electron will occupy the lowest energy orbital available. The Aufbau principle helps us determine the order in which electrons fill up an atom's orbitals. So 1s gets filled first, then the 2s, then the 2p, followed by 3s and 3p, then 4s, then 3d, then 4p, then 5s, 4d, 5p, and so on. The energy levels and the orbitals can be arranged in this particular pattern. The arrows show the order in which the orbitals will be filled when you're filling up an atom with electrons. On the bottom here, we have listed the order from lowest potential energy to highest potential energy for each of the subshells. On the periodic table, we see that the subshells exist in this pattern. This coincides with the diagram that we just saw. Now, we will start talking about orbital diagrams. This is a pictorial way of representing the electrons inside one atom. So when we draw orbital diagrams, what we do is we arrange boxes that represent the orbitals inside that atom. And then we draw arrows inside each of the boxes to represent the electrons. One arrow equals one electron. Notice how on the left-hand side we have increasing energy. This shows how the potential energy of each of these orbitals is increasing. First we see the 1s orbital with the lowest potential energy. Next we see energy level 2, which is broken down into the 2s orbital and the 2p orbitals. Then we see the third energy level, which is broken down into the 3s orbital and the 3p orbitals, and then the 3d orbitals. Notice how the 3d orbital is slightly higher than the 4s orbital. Where else do we see overlaps? So hydrogen has only one electron. It would fall into the 1s orbital, and we would put an arrow pointing up. Helium has two electrons. We would put both of them into the 1s orbital. One of the arrows will point up, and the other arrow will point down to represent opposite spins. Lithium would have three electrons. One electron would point up, and the other one would point down, and the third electron would go into the 2s orbital pointing up. Here we see how the electrons would be placed into the 2p orbitals for boron, carbon, nitrogen, and oxygen. Notice how when we have multiple electrons, we don't put two electrons into the same orbital. Instead, what we do is we place one electron in each of the orbitals until each orbital has at least one electron. Notice how each of the electrons in these 3p orbitals all have the same spin. It is only when we have our fourth electron that we place it into the first orbital with the opposite spin. This brings us to our next rule. The next rule is called the pauli exclusion principle. This says that no two electrons inside the same atom can have the same set of four quantum numbers. So let's take, for example, nitrogen. How many electrons are there in a nitrogen atom? 7. Each one of those 7 electrons has a different set of four quantum numbers. This is the four quantum numbers for the first electron in nitrogen. This is for the second, that's the third, fourth, fifth, sixth, and seventh. So the first electron is placed where hydrogen would be, and the second electron will be placed where helium is. The third, the fourth, the fifth, sixth, and seventh electrons are all placed in order according to the periodic table. Let us remind you again that each subshell can be broken down into multiple orbitals. So although the S subshell only has one orbital in each subshell, the P subshell has 3 orbitals in it. The D subshell has 5 orbitals in it, and the F subshell has 7 orbitals in it. So each orbital holds up to 2 electrons. So since the P subshell has 3 orbitals, there are 6 spots to place 6 electrons. Since the D subshell has 5 orbitals, there are 10 spots to put 10 electrons. And since the F subshell has 7 orbitals, there are 14 spots to put 14 electrons. Hund's rule says this: when filling in electrons into a subshell with multiple orbitals, you must put one electron in each orbital with the same spin first, before adding a second electron into any of the orbitals. Because of the Pauli exclusion principle, when the second electron is added to any orbital, that second electron must have the opposite spin. This is why you see a plus half and a negative half occurring in the first 2 electrons placed in nitrogen. The first electron placed in nitrogen will have a positive spin, and the second electron put into nitrogen will have a negative spin. These 2 electrons will be found in the 1s orbital. The next 2 electrons placed into nitrogen will be placed into the 2s orbital. The first one will have a positive spin, and the second one will have a negative spin. The next 3 electrons all have a positive half spin. This follows Hund's rule. They all have a positive half spin because each of those 3 electrons went into a different orbital. So this concludes our lesson on the 3 rules of quantum mechanics. Thanks for listening.